From one planet to 5,000, the universe just got bigger. In 1992, we confirmed the first planet beyond our solar system. Just one. Now, we know of over 5,000. Some are gas giants hugging their stars. Others are rocky and Earth-sized, orbiting suns not unlike our own. But in 2025, everything is set to change. NASA and its partners are preparing for a wave of new discoveries, not just finding more exoplanets, but uncovering what surrounds them, their atmospheres, their chemistry, and perhaps their habitability. For the first time in history, we may detect something that feels familiar. Oxygen, water vapor, methane, even complex carbon-based molecules floating in alien skies, orbiting distant stars. These aren't dreams. They're within reach, thanks to telescopes like the James Webb Space Telescope and the soon-to-launch Nancy Grace Roman Telescope. In the next few years, we won't just catalog distant worlds. We'll analyze them deeply, layer by layer, molecule by molecule. In this video, we'll explore what NASA is likely to discover around exoplanets identified in 2025, from blazing hot Jupiters to ocean-covered Earth-like planets. We'll ask, what might we find? And what happens if we find life? This is not science fiction. This is the future unfolding right now. 30 years ago, the idea of planets orbiting distant stars was mostly science fiction. Now, it's a scientific reality, with thousands of confirmed worlds and hundreds more discovered every year. In 1992, astronomers confirmed the first exoplanets, two rocky bodies orbiting a pulsar. It wasn't what anyone expected, but it proved something vital. Other planets exist, and if they exist there, they must exist elsewhere. Then, in 1995, scientists found 51 Pegasi b, a massive gas giant orbiting a sun-like star. It was hot, fast, and close to its star, a type we had never imagined. Our understanding of planetary systems began to unravel and expand. The discovery snowballed. In 2009, NASA launched Kepler, a space telescope that stared at a single patch of sky for years. It found thousands of planets by measuring tiny dips in starlight, signs that something was crossing in front. Thanks to Kepler, we learned that planets are not rare. They're common, and many are Earth-sized. Next came TESS, launched in 2018. It scanned nearly the entire sky, focusing on stars close to Earth. Its mission? To find promising new planets that could be studied in more detail. Not just found, but understood. That's where the James Webb Space Telescope enters the story. Launched in 2021, it uses powerful infrared instruments to look into alien atmospheres. It's already found carbon dioxide, water vapor, and signs of complex chemistry, all light years away. Now, NASA is preparing for its next tool, the Nancy Grace Roman Space Telescope, launching later this decade. It will scan the galaxy with unmatched precision, using gravitational microlensing to detect planets even Earth-based observatories can't see. And in 2025, all of this will converge. New planets will be found. Known planets will be analyzed. And for the first time, we'll start to build a real picture of alien worlds. This journey, from a few hot giants to thousands of distant Earths, took decades of work, failure, and vision. But it brought us to this moment. NASA isn't just searching anymore. It's finally ready to start understanding what's really out there. 2025 isn't just another year on the calendar. For exoplanet science, it's a turning point. By then, NASA and its partners expect to catalog hundreds, possibly thousands, of new exoplanets. Not just gas giants, not just mysterious blips in data. We're talking about rocky worlds, super-Earths, mini-Neptunes, entire families of planets orbiting distant stars. The key drivers of this breakthrough? First, test data maturing. By 2025, the full dataset from the Transiting Exoplanet Survey satellite will have been processed, verified, and refined, giving scientists a goldmine of planet candidates. Many orbit stars close enough for detailed follow-up, close enough to study, close enough to matter. Second, the James Webb Space Telescope, fully online and focused. Webb will be deep into its mission, capturing the infrared fingerprints of alien atmospheres. Scientists expect to detect water vapor, carbon dioxide, methane, and even oxygen, elements that may point to habitability or something more. In 2025, we'll likely see the first ever side-by-side comparisons of exoplanet atmospheres. Multiple worlds with chemical breakdowns, temperatures, and pressure profiles. Some will be wildly exotic, others eerily Earth-like. Then comes the Nancy Grace Roman Space Telescope. Scheduled to launch by late 2025, Roman will offer wide-field imaging of the Milky Way, capable of spotting planets we couldn't find before using gravitational microlensing. It may even detect rogue planets, drifting through space unbound by any star. Lonely worlds, dark and cold, yet real. NASA also plans to test advanced coronagraphs, tools that block out a star's light so we can directly image orbiting planets. For the first time, we might see an Earth-sized world beside a sun-like star, not as a signal, but as a faint point of light. 2025 isn't just about more planets. It's about better data. Astronomers hope to detect clouds, hazes, and even weather patterns. We might spot high-altitude clouds of silicate dust or metal-rich atmospheres where it rains molten iron. Some planets will rotate slowly. Others might be tidally locked, with one permanent day and one eternal night. We could map thermal shifts across their surfaces, from scorched hot sides to frozen dark zones. And in a few rare cases, we might glimpse the color of a sunset on another world. And then comes the big leap: biosignatures. NASA and its partners are refining models that can identify suspicious chemical combinations, like methane coexisting with oxygen or persistent levels of carbon monoxide alongside water vapor. These combinations don't guarantee life, but they're hard to explain without it. It's entirely possible that by 2025, a planet will trigger alarm bells. Not proof, not yet, but indications. Hints, enough to say, something strange is happening here. And beyond that, surprises. History tells us science never moves in a straight line. Some planets will break the rules. Some will reveal rings, moons, or bizarre orbital paths. We may even discover multi-planet systems where more than one world orbits in the habitable zone. 2025 is the start of something huge. It marks the moment we move beyond finding planets and begin truly understanding what they're like. Worlds with storms, with winds, with climates and chemistry we've never imagined. World we may someday visit or call home. Finding a planet is only the beginning. The real question is, what's around it? An atmosphere can reveal almost everything. It tells us about pressure, temperature, chemistry, even signs of habitability or life. That's why NASA is laser-focused on collecting atmospheric data. Using telescopes like James Webb, scientists observe exoplanets during transits when a planet crosses in front of its star. Some starlight filters through the atmosphere, leaving behind chemical fingerprints. We decode those patterns to identify the gases present. So, what exactly are we looking for? 1. Water vapor is essential for life as we know it. Water vapor tells us a planet may have clouds, rain, maybe even oceans. It's not confirmation of life, but it makes a world more promising. 2. Carbon dioxide and methane CO2 helps us understand the greenhouse effect. Methane is more complicated. On Earth, it's released by both volcanoes and living organisms. If we detect both gases together, especially without clear geological explanation, that's intriguing. 3. Oxygen and ozone-oxygen doesn't last unless something is replenishing it, like photosynthetic life. Ozone, formed from oxygen, can also be a signpost. In the right mix, these gases might suggest biological activity. 4. Ammonia, carbon monoxide, and others. NASA also tracks trace gases like ammonia or carbon monoxide. On certain planets, they could point to volcanism, geochemical reactions, or even microbial life. But atmospheres aren't just about gases. 5. Clouds and hazes. By analyzing light scattering, we detect cloud layers or hazes, possibly of sulfur, hydrocarbons, or even metal. Clouds affect climate, temperature, and how much of the planet we can see. 6. Thermal profiles. Some telescopes map heat distribution, revealing if a planet has winds, seasons, or day-night extremes. For example, hot Jupiters with poor heat circulation can be scorching on one side and frozen on the other. 7. Albedo and reflectivity. A planet's reflectivity tells us whether it's cloud-covered, icy, or bare rock. High albedo could suggest cloud systems, while low reflectivity might mean lava plains or dense atmospheres. Once data is collected, scientists feed it into computer models to simulate possible conditions. They test hundreds of variations, tweaking chemistry, pressure, and sunlight to see what matches the readings. Some models suggest steam-rich worlds with global oceans. Others hint at desert planets with thick CO2 blankets. Still others point to gas giants with swirling ammonia clouds or iron rain. But what scientists truly want to find is a pattern. Imagine multiple Earth-sized planets, each with hints of water, each with oxygen, each with similar atmospheric balance. That's not a coincidence. That's a clue. And then there's the concept of disequilibrium chemistry. This happens when a planet's gases appear in combinations that shouldn't be stable, unless something is constantly producing them. Think of methane and oxygen together. They should react and disappear. If they're both present in stable concentrations, something must be maintaining them. And that something could be life. It's the ultimate scientific goal. Chemical imbalances that hint at biology. Still, NASA is careful. Biosignatures can be mimicked by non-living processes like sunlight-driven reactions or volcanic activity. So they rely on cross-checks, simulations, and global collaborations to confirm findings. Because when we finally do find a planet that can't be explained away, it changes everything. What NASA is looking for isn't just chemistry. It's context, a full picture, a signal in the noise that whispers across space. This world might not be alone. Not all planets are created equal. Some are scorching gas giants, locked in tight orbits. Some are frozen ice balls, drifting far from any warmth. But a few, just a few, might sit in the Goldilocks zone. Not too hot, not too cold, just right for liquid water. NASA defines a habitable world as one that could, in theory, support life. It doesn't need trees, lakes, or cities. It just needs the potential, the ingredients for biology to exist or emerge. So, what makes a planet potentially habitable? First, temperature. It needs to orbit in the star's habitable zone, the sweet spot where water can stay liquid. Too close, and it's a pressure cooker. Too far, and everything freezes. Second, size and structure. We want rocky planets, not puffy gas giants. Something Earth-sized or slightly bigger, with solid ground, stable gravity, and a surface you could, in theory, stand on. Third, atmosphere. A planet needs a shield to trap warmth, block radiation, and maybe hold the gases life depends on. Oxygen, carbon dioxide, even water vapor. Fourth, magnetic field. Invisible but vital. It deflects deadly solar wind and keeps the atmosphere from being stripped away, the fate of Mars. Fifth, orbital stability. A planet needs time. Stable conditions over billions of years allow life to form, evolve, and survive. In 2025, NASA expects to find multiple candidates that check these boxes. Some will orbit red dwarf stars, cooler, smaller stars that make up most of the galaxy. They have wide habitable zones, but they're also known for violent flares. So if a planet still holds an atmosphere around one of these stars, that's major. Others may orbit sun-like stars, rare but extremely exciting. Those systems are most like our own. If we find a planet with Earth's mass, an atmosphere, and signs of water orbiting a quiet star, it changes everything. That world becomes a target for future telescopes, future missions, even dreams of future travel. Because a habitable planet isn't just a dot in the sky. It's a mirror, a question, a possible second Earth waiting to be found. life leaves traces. On Earth, it's oxygen, methane, chlorophyll, waste products. If alien life exists, even in microbial form, it might leave chemical footprints behind. That's why NASA is hunting for biosignatures, signals in a planet's atmosphere or surface that can't easily be explained without biology. But spotting life from light years away isn't simple. It starts with spectroscopy, breaking down starlight that's passed through a planet's atmosphere during transit. Each gas absorbs light at specific wavelengths, leaving a fingerprint that scientists can read. Some molecules, like oxygen, are promising. On Earth, oxygen doesn't last long unless constantly replenished by living organisms. Others, like methane, can come from both volcanoes and microbes. But if we see methane and oxygen together in large amounts, it becomes very suspicious. Why? Because those gases destroy each other over time. If they're both present in stable concentrations, something must be recreating them. On Earth, that something is life. NASA is also exploring more exotic markers, gases like nitrous oxide, isoprene, or phosphine, which are difficult to produce without biological processes. These are molecules you wouldn't expect to find naturally, but could emerge from alien metabolisms. Still, gases aren't the only clue. Some scientists believe that microbial life could alter a planet's reflectivity, temperature profile, or even color. A greenish tinge, seasonal variation, or spectral shifts might all hint at photosynthesis or some alien biological cycle. And then there are temporal biosignatures, changes over time. Does a planet's atmosphere evolve like ours does with seasons? Do gases appear and disappear in patterns? But science demands caution. Many biosignatures have false positives, non-living processes that mimic life. Volcanoes, UV radiation, and even strange chemistry can create misleading signals. That's why NASA emphasizes combinations, a full atmospheric profile consistent with a living process. For example, water vapor, carbon dioxide, methane, and oxygen, together in stable ratios. 2025 may not deliver proof of alien life, but it could spotlight planets we can't explain, places where something's happening that doesn't make sense. And in science, doesn't make sense is the first step toward discovery. No spacecraft, no photos, just a signal and light. A chemical whisper from across the stars, saying, I am not alone. 2025 is just the beginning. The discoveries of that year will do more than reveal new worlds. They'll shape the roadmap for everything that comes next. NASA is already planning a new generation of missions. Bigger, more powerful, and more focused than ever before. Leading this charge is the Nancy Grace Roman Space Telescope. Launching in the mid-2020s, it will use gravitational microlensing to find planets that other techniques miss, especially ones farther from their stars, or even rogue planets drifting between systems. It will also test coronagraph technology, laying the foundation for direct imaging of exoplanets. But this is just the start. NASA is developing concepts like HabEx and LUVOIR, massive telescopes that could directly observe Earth-like planets, analyze their atmospheres, and detect seasonal changes or even surface features like continents or clouds. They may be our best chance at discovering the first true Earth twin. Then there are bold ideas. Interstellar probes, launched by lasers, traveling at a fraction of light speed to nearby stars like Proxima Centauri. Projects like Breakthrough Starshot are already testing the technology. Small spacecraft, faster than anything we've ever built, reaching another solar system in just a few decades. Even more ambitious, next-gen propulsion, nuclear engines, ion drives, solar sails, and theoretical designs based on fusion or antimatter. One day, they could carry robotic explorers or even humans to other star systems. But we're not there yet. First, we need better data. And for that, we need bigger eyes. Future telescopes will focus on direct imaging, capturing light from the planet itself, not just its transit shadow. This could reveal weather patterns, seasonal shifts, or even signs of alien civilizations. Yes, technosignatures. NASA SETI, and other groups are looking for signs of technology. Lasers, radio waves, or pollutants in an atmosphere that can't form naturally. Because finding planets is only step one. The real goal is understanding what and who might live on them. 2025 will ignite the spark. But what follows could be the biggest discovery in human history. A second Earth, a new perspective, and the beginning of a story far larger than our own. The search for life beyond Earth isn't just science. It's a mirror, a way of asking who we are and where we fit in the vastness of space. For centuries, we looked at the stars and wondered. Now, with missions like TESS, James Webb, and the discoveries coming in 2025, we're starting to get answers. We've moved from guessing to detecting, from detecting to analyzing, and from analyzing to imagining what might be out there. Maybe we'll find water. Maybe we'll find clouds. Maybe we'll find atmospheres so strange they'll reshape what we believe life can be. Maybe we'll find nothing, and even that will teach us something. Or maybe, just maybe, we'll find something alive. 2025 could be the year that changes everything. And if it does, we'll look back at this moment as the time we started to see our universe not as empty, but full of worlds, full of stories, full of possibilities, and maybe someday full of neighbors. If you want to follow this journey, subscribe to the channel, hit like, and share this video with anyone who still looks up and dreams. Because the search isn't over, it's just beginning.